This chapter begins on a very practical note, talking about nuclear energy from nuclear fission. And then it gets a little bit theoretical, talking about nuclear fusion, where it's actually going on in stars, but where we hope someday to be able to do it here on Earth to generate electrical energy. And then it gets increasingly theoretical and philosophical. Nuclear fission, you'll recall, is the splitting of a large nucleus into pieces. And the kind of nuclear fission we're talking about is the kind where our bullet is going to be a neutron. And we're going to aim it at a large nucleus. Large nuclei can sometimes be split. Smaller nuclei have to be fused together to reach that stable region in the middle of that graph in the last chapter, where you have the most binding energy in the region of iron. Now, just because you hit a nucleus with a neutron doesn't mean it's going to split that bigger nucleus. In fact, as far as nuclear energy is concerned, the only two nuclides of note, that are practical in this regard is the uranium-235 nucleus and plutonium-239 nucleus. There are small amounts of fission that can happen from uranium-234, but it's really not worth talking about. So if you want to generate electrical energy from steam produced by nuclear fission, you need uranium-235, which you might recall is a very small percentage of the naturally occurring uranium on the planet. Most of the uranium on the planet, 99.3% of it, is uranium-238. When a neutron hits uranium-238, it just sticks. And there are practical applications of that, including as a step in the making of breeder reactors. That's another story. But for our purposes, the only two nuclei that will fission to produce the energy that we want is uranium-235 and a non-naturally occurring isotope of plutonium, plutonium-239. So keep in mind that the energy, again, comes from the nuclear mass defect. If you add up the mass of the reactants, if you look at equation 30.2 down here, in this equation, it's interesting, in this equation, your reactants are the neutron and the uranium-235 nucleus. So you have a total of 236 nucleons on the left side. On the right side, you have an isotope of barium, an isotope of krypton, and 3 neutrons. So if you add up the mass of your particles on the left, subtract from that the mass of the particles on the right, you'll notice that some of your mass is not accounted for. The stuff on the right doesn't equal the mass of the stuff on the right. And that's because some of the original mass is converted into energy, E equals mc squared, which you can convert into joules of energy, or you can convert into mega electron volts of energy. And you can see that for each nucleus, you get about 200 mega electron volts when you split a uranium-235 nucleus. Oftentimes, we like to compare this to other nuclear reactions, and we divide it by the total number of nucleons to get our MeVs per nucleon, which is a more fair way to compare the energy produced from different kinds of collisions. Now, continuing to look at equation 30.2. Barium and krypton are examples of many, many possible combinations of what we call daughter products or fission fragments. This is the nuclear waste material that we have to store somewhere. When every year we recycle or we remove about 1/3 of our uranium fuel rods from nuclear reactors, and that's because they contain high levels of these daughter products, such as barium and krypton. And that's one of the political issues, is about safely storing them. And where should we safely store them? It's a political issue, not so much a physics issue. It has to do with the Yucca Mountain in Nevada. Now you'll notice that you also produce 3 neutrons. Some fissions produce 2, some produce 3. The point being that these neutrons that are produced can actually hit other uranium-235 nuclei or plutonium-239 nuclei and create more daughter products and more neutrons and more energy. We call this a chain reaction. Now, our conception of what's going on, if indeed you are able to look at, is that we have a slow neutron. That's kind of important. Fast neutrons have a tendency not to split or to miss the nucleus entirely or to glance off. But a slow neutron has the chance of temporarily being captured, turning into a metastable uranium-236, picture B, which begins to oscillate, vibrate, until it splits in half into your daughter products, X and Y, and releases 2 or 3 neutrons and a whole lot of energy, considering it's just a nucleus. So please notice what's going on. You have one atom, or nucleus, turning into 2 smaller ones, and some neutrons, and a lot of energy. If we look at example 30.1, the math problem, calculate the total energy released if 1 kilogram of uranium-235 undergoes fission, taking the disintegration's energy per event to be Q equals 208 MeVs. The previous page we estimated about 210 MeVs per nucleus. And then we got part B. How many kilograms would it be needed to satisfy the world's annual energy consumption, which is about 4 times 10 to the 20th joules. So the first thing that we're going to do is go from grams to moles to nuclei. One way to do that is to get our moles to cancel out, because we have Avogadro's number per mole, and from the periodic table we have 235 grams per mole. So the moles cancel. We multiply that by our sample of 1,000 grams, and we get a total number of 2.56 nuclei of uranium-235. Then we multiply that number of nuclei times the energy that each nuclei potentially can release, about 210, and we're using 208 MeVs per nucleus. So that gets me my entire amount of energy from my 1,000 original nuclei, 5.32 times 10 to the 26 mega electron volts. Now, if we want to compare that to the total energy consumption on the planet in a year, we need to divide that amount of energy into the total, but we need to be consistent with our units. We need to multiply by a conversion factor. Here's my conversion factor. This is how many joules there are in an electron volt. And you could calculate that if you used E equals mc squared and 931.5. In any case, we find out that you would need 5 million kilograms. Or we could say 5,000 metric tons of uranium, which really isn't all that much. 5,000 metric tons. A metric ton is 1,000 kilograms, which is roughly 2,200 pounds, and a normal ton is 2,000 pounds. Now, the goal in a nuclear reactor is not to have all your energy released at once. You would hate it when that happens, but to have the energy released in a regular fashion for a long period of time. And so when you get a chain reaction where one neutron strikes a uranium-235 in the upper left of the picture, you get your two daughter products, which are going to have to be stored somewhere someday. You get three neutrons, which strike three nuclei, which split up, and each of those produces three more neutrons. And so now you're striking 9 uranium-235 nuclei, and then 27, and then 81. And this happens very, very, very quickly. And now you're producing a significant amount of energy, which you can use to turn water into steam, and steam to flow past a turbine generator, which will rotate coils of wire in a magnetic field, think back to chapter 20, like a generator, and generate electrical energy. This is a chain reaction. Now you can see a couple of things. You need to have enough uranium-235 in one place so that when your neutrons are produced, there's a high likelihood that they'll strike a 235 nuclei. And that amount of uranium-235 is 4 to 5%. Remember, a nuclear weapon, an atomic bomb would need over 90% uranium-235 in a sample of uranium. So this is very important. A nuclear reactor cannot blow up like a nuclear bomb because it's only 5% 235, not 90%. I wonder if that's going to be a test question. Common misperception that nuclear reactors can blow up like a bomb. Another thing you'll notice here is that if you want to control the nuclear reaction, if you want to generate more energy because there's a big demand, maybe it's a really, really hot July day and everybody's running their air conditioners, or you want to slow it down because you don't need as much energy, the key is to control the neutrons. If you can absorb the neutrons before they strike 235 nuclei, you can slow the reaction down. Now, if you look in the picture in the upper right, the control rods are made out of a material, often cadmium, that absorbs neutrons. And the control rods are in between the fuel rods. The fuel rods contain marble-sized pellets of uranium-235. And when the control rods are in the position that you see in the picture, obviously you don't have a critical mass, enough uranium-235 in one place, because the fuel rods are separated by all of the control rods. But if you lift the control rods out from above, lift them out, then they're not absorbing neutrons. And now you can have a sustained chain reaction. Notice also that you have radiation shields, large amounts of lead and concrete to keep any radiation inside this vessel. You also have a moderator. A moderator would be a substance, often just water, that will slow the neutrons down so that they have a higher likelihood of being able to split 235 nuclei. And not showing is also a substance that would be a reflector. so that instead of neutrons leaving the core, they're redirected back into the core, which allows the operators to very easily, or I should say carefully, have total control almost of all of the neutrons being produced. They're all inside that core. Now, one of the advantages of lifting the control rods out, and this is true of reactors in the United States, is that if something were to go wrong, if there were to be a sudden massive power outage for some reason, or something would knock out the electricity to the power plant, what would happen is the control rods, under the influence of gravity, would just fall back into the core and absorb the neutrons, shut down the chain reaction, and you would not have any damage or any radiation release from radioactive steam that might boil that moderating fluid. It's a passive system because you can't turn off gravity. Now, the control of these neutrons is represented by this letter K, called the reproduction constant. It's defined as the average number of neutrons from each fission event that will cause another event. And so as long as K is about 1, just about 1, you are producing just enough neutrons to keep the reaction going. And we say that the reactor is now critical. It's operating. It's generating heat. And you need to carry that heat away to turn your water into steam. And various things will affect that value of K mathematically in the equation where they determine K. They need to know the size of the reactor. They need to know the likelihood of slow neutrons being produced as a result of your moderator, which is often graphite or heavy water. And all of these things have to be, you have to know how many neutrons might not be reflected back in by the reflector. And all of these things go into carefully calculating and then regulating neutrons. Now, some of our modern ideas are to replace the water, which easily turns into steam. And of course, steam produces a tremendous amount of pressure, which makes the plumbing pretty tricky, holding on to that steam until you want it to expand in the turbine blades. They're thinking about using liquid sodium, light metal reactors, which would not have that plumbing issue. But of course, you like water because it has such a high specific heat for carrying heat away. Now, if you look at this next paragraph, it's kind of interesting to note that the health risk, and I'm quoting the text here, of living within 5 miles of a nuclear reactor for 50 years is no greater than the risk of smoking 1.4 cigarettes during the course of that time, or drinking half a liter of wine, or traveling 240 kilometers by car, or flying almost 10,000 kilometers by jet all the way across continent, or having a chest x-ray. Each of those activities is estimated to increase a person's chance of dying in a given year by about 1 in a million. So you might wonder, why is there so much concern and sometimes outright anger about nuclear reactors and nuclear energy? And your text, which is not known for being terribly political or necessarily biased in the political arena, a lot of people are very concerned about things they don't fully understand, because this is all going on, in terms of nuclei. It's not like a chunk of carbon, or a gallon of crude oil or something like that. And of course, unfortunately, lots of people, when they think nuclear, immediately think of nuclear bombs and mushroom clouds. And of course, we already said that a nuclear reactor is nowhere close to having the high enough percentage you need for a nuclear bomb. And it has many other passive safety features as well. Even if the heat were to begin to accumulate because you're not removing the water fast enough, that would cause your nuclear core to expand. And when it expands, then the uranium is not as dense as it needs to be to sustain a chain reaction. And we might mention that every way of generating electrical energy has risks. Solar panels are made out of toxic materials, have to be regularly cleaned, really don't last all that long, are only good when the sun is shining, take up a lot of space. Windmills, there's more and more of them. Some people don't like looking at them, and if you live nearby, you can hear them. And they have a tendency to chop up larger birds. And if you're a bird, you hate it when that happens. And of course, you got to have wind. So everything has got a risk. But thinking that a nuclear reactor would be like a nuclear bomb is kind of like thinking every time you plug something into the electrical outlet, you're thinking about an electric chair. They're very, very, very different. One good thing about nuclear energy is it doesn't release carbon dioxide. And so if you're really concerned about carbon dioxide and you think it's a significant global warming kind of greenhouse gas, this is one way to eliminate that. Because one nuclear power plant takes the place of a whole lot of coal and oil. I did mention breeder reactors, and this raises the question, well, how much longer do we have before we run out of uranium? Well, remember that uranium-238 that only absorbs a neutron? Well, when uranium-238 absorbs a neutron, it turns into uranium-239, and uranium-239 can undergo a beta decay to become plutonium-239, double beta. And plutonium-239 is a fissile fuel. It's a nuclei that can be split. So if you were to design your reactor so that all your uranium-238, the 95% of your fuel that's uranium-238, is absorbing these neutrons, you can create all the plutonium you need and put them right back in the nuclear reactor rather than try to store it somewhere in a repository. And then you've got well over 1,000 years of fuel left to generate electricity from nuclear. And of course, we can also find lots of uranium, surprisingly, not just in the Earth's crust in various deposits. Like there's one very rich deposit in South Africa that's so rich it actually has its own melting going on in the heat that it's generating. It's like a natural nuclear reactor going on. But there are billions of metric tons of uranium in the Earth's oceans if you can separate it. And all those things get there from erosion, from rivers and streams. Now, I should say one other thing about nuclear reactors. American nuclear reactors are called pressurized water reactors, PWRs. And that's because in the first loop, you use water under pressure to carry the heat away from the nuclear core. That heat in that water that is under pressure, so it always stays liquid, goes through a heat exchanger where all that heat then is absorbed by water that's self-contained in a second loop, and that's the water that turns to steam. And when that water turns to steam, it runs turbine blades to generate electricity, which cools it down, and it becomes a liquid again, and that goes to a third heat exchanger, where you bring in water from the environment, which cools down the water self-contained in the second loop, which then flows back to the first loop and cools that water down that's self-contained in the first loop. So the water that's going through the nuclear core is 2 loops away from the environment. And by regulations, the water that's in that third loop that we bring in from the environment, that water would go to a cooling tower that uses Bernoulli's principle to cool it down through evaporation. And we talked about this way back when we talked about Bernoulli's principle, where the air is faster at the top of the cooling tower than it is at the bottom. Remember, a cooling tower is about 2/3 the size of an arch, the St. Louis Arch. Sometimes they just let the water sit in a holding pond for a bit, but they don't return it to the environment, let's say the river or something, until it's within a fraction of a degree of the temperature that they brought it in from. That's another safety precaution. And Russia doesn't have all of these precautions because it's too much trouble, it costs too much money, and again, in a communist worldview and political system, you're willing to sacrifice people for the sake of the state. And in a democratic republic, the government's supposed to be established to serve the people, the other way around. Nuclear fusion. This is a good example, again, where, unfortunately, like with nuclear fission, we have been able to develop a military use of this before we've developed a commercial use. Remember back in 1945, we dropped 2 bombs on Hiroshima and Nagasaki, which very abruptly ended World War II, probably saving 1 million American lives who would have had to assault Japan, and probably 3 or more times that many Japanese citizens. But the point is, the war ended, but it did cost 60 to 100,000 lives in each city. That was an atomic bomb. One atomic bomb on one of the cities got the critical mass of uranium in one place at the right time by shooting a wedge of uranium from the back of the bomb using a little bit of dynamite towards the front of the bomb where the rest of the uranium was to get your critical mass. And there were no control rods or anything like that, and you get the huge amount of energy. The other bomb on the other city was a different design. It was rounder, and it had a bunch of pie-shaped wedges that all fired into the center at the same time. And these were under the code name of Fat Man and Little Boy. Fat Man and Little Boy. The little boy was the long, skinny one. Fat Man was the round one. And these were references, if the Japanese had been listening into our communications, they would have thought we would have been talking about Churchill and Roosevelt. Now, fusion, again, we don't have any fusion reactors generating electricity. It would be nice because you get a lot more bang for your buck, a lot more energy per nucleon, and you don't produce the radioactive material. This is the way stars do it, and stars are kind of hot. Hopefully you realize that. Well, we have to be able to create temperatures as hot as stars in order to get small nuclei to fuse together and in the process release a lot of energy. And we're able to do that, but on an extremely small scale with super powerful lasers. And then you might say, well, what kind of container are you going to put this plasma that you create? That's a fourth state of matter. What kind of container are you going to put it in that can hold something that's as hot as a star? And the answer is not Tupperware. Instead, we have to suspend it in a magnetic field, kind of like a huge, gigantic electromagnet. that would be bigger than a classroom in size. It's like a donut, a hollow donut, where you have wires wrapped around the outside of the donut, creating this electromagnetic field. And you can see the chain reaction, 30.3. Not the chain reaction, excuse me, the fusion reaction. We take small nuclei like protium and protium, hydrogen 1 plus hydrogen 1, or protium plus deuterium, hydrogen 1 plus hydrogen 2. Different ways to do this with really small nuclei to produce an awful lot of energy. And I've been following the progress, if you want to call it that, of fusion for a long time. And I can't tell you how many times I've heard them say, well, we're at the break-even point. We're at the break-even point. Give us another 10 years. And I think we're a little bit past the break-even point where the amount of electrical energy we put in to our lasers and our magnetic confinement is equal to the electrical energy we get out. Now, at some point, it would be nice to have another way of producing energy. And that's up here. Notice where I have highlighted right here, positron combined with electrons to... Remember, positrons are the antiparticle to the electrons. And so this is a antimatter-matter reaction. And when you have a matter-antimatter reaction, it produces a huge amount of energy in a process that is called annihilation. And supposedly this is how the Starship Enterprise in the TV and movie series Star Trek is able to generate the energy to warp space to travel the great distances that it can. And we have dropped some fusion bombs. Fortunately, and let's pray this never happens, not in a military or wartime sense. Certainly having them has maybe made people afraid to attack us. But when we've tested some of these were in the Bikini Island Atoll in the Pacific, and we basically told the people living on a couple of these islands, we're going to evacuate you, you all have to leave, we're going to blow up your island. And we surrounded it with old ships from World War II to help with the study of this. If you're going to blow up something like this, you might as well do as much science as you can. And they dropped the bombs and did all of their studies and destroyed these old ships and been monitoring this place ever since. And only in the last couple of years have I started to see in the news that the inhabitants from over 50 years ago, some of the descendants at least, or the older people now, are saying, can we go back to our islands now? So fusion reactors is where you're fusing small nuclei to make bigger ones. And if you look at this first thing that I've highlighted up here, for example, if deuterium, the isotope of hydrogen, consisting of a proton and a neutron, were used as the fuel, it would take 0.06 of a gram. We could extract it from 1 gallon of water, and it cost 4 cents. That is pretty cheap to do the extraction process. There's another isotope, tritium, 1 proton, 2 neutrons. That is a bit radioactive, has a half-life of, if I remember correctly, like about 12.7 years. I've worked with tritium once, never worked with deuterium, heavy water, but instead of H2O, which are 2 hydrogen 1 nuclei and oxygen, heavy water would be 2 deuterium, 2 H2 hydrogens and an oxygen. And you don't get very many radioactive materials formed. That's a plus. The end product of fusion, is helium. And so we'd be able to fill up a lot of balloons. And actually, we use helium in a lot of research. And of course, the part of the challenge is you're making these nuclei, which are positively charged. You want them to fuse, and there's going to be a price to pay, and that is that they repel each other. They have that Coulombic repulsive force. So you've got to have enough energy to overcome that, and then enough energy to fuse together. And so we're creating temperatures when we do this hotter than the interior of the sun. And this is called plasma. And here's what a tokamak, a huge big donut, would look like. It'd be about, if you were to stand next to that, it would be about twice as tall as you. And you would be wrapping wires around there to create your electromagnetic field to suspend the plasma in that ring so it does not touch the surface. And the last thing, you'll notice Philo T. Farnsworth down here. Every day on my way from Rexburg, Idaho, down to Idaho Falls to do my research, we traveled through a little town called Rigby, Idaho. I think it had less than 5,000 people, but they had a sign out front that said, "Home of Philo T. Farnsworth," the inventor of the TV. Well, he invented the cathode ray tube that was used in those old-fashioned TVs. And you can see here that you can get an awful lot of mega electron volts. By here, I mean in finding the nuclear mass defect. The mass you start with is more than the mass you end with. So when you subtract, your nuclear mass defect is right here. If you convert that into energy, you get 18.35 MeVs. Well, you might say, well, wait a minute, uranium did 200 MeVs per nucleus. I think we used 208. Well, if you divide that by the number of nucleons, one neutron striking a 235, you divide that by 236, you get a much, much, much smaller number. And here, of course, 18.35, you're dividing it by just a few nucleons, 5. And we'll pick up later.